Fact 1. A black hole is a spatial region where gravity is so powerful that its boundary cannot be crossed even by light. This boundary is termed the event horizon. Everything that ends up inside loses its causal connection with the external world. The radius is not dependent on density, but solely on mass, and it is described by the Schwarzschild formula R equals 2gm by c squared. The Sun's hypothetical horizon would be around 3 kilometers, while Earth's would be approximately 9 millimeters. It is significant that black holes do not vacuum space. An object in a safe orbit will rotate stably, as it would around any mass. Near the horizon, time passes more slowly, gravitational time dilation, and light experiences a significant redshift. A distant observer will never see a body cross the horizon. Its image will freeze and dim until it becomes invisible. The most secure way a black hole is born is through the core collapse of a highly massive star after it has exhausted its thermonuclear fuel. When the outward pressure from degenerate gas and neutrons can no longer counteract the weight of the outer layers, gravity becomes the dominant force. The star's mass and composition determine whether this leads to a supernova or a quiet direct collapse into a black hole. The mass thresholds are affected by metallicity and mass lost via stellar winds. Current estimates indicate that the initial star should have a mass of tens of solar masses, and the core left behind should be about 2 to 3 solar masses. In binary systems, a phenomenon called fallback can happen where some of the material ejected returns, thereby increasing the mass of the newly formed hole. This evolutionary process helps explain why many X-ray binary systems exist.
Hecho 3. En los centros de la mayoría de las galaxias grandes se esconden agujeros negros supermasivos, con masas que van desde millones hasta decenas de miles de millones de masas solares. En la Vía Láctea, el objeto central Sagitario A' pesa alrededor de 4 millones de masas solares. Su presencia se confirma por las órbitas de las estrellas que a lo largo de años de observación dibujan elipses alargadas alrededor de un centro invisible. En la galaxia M87, el agujero negro supermasivo alcanza aproximadamente 6.5 mil millones de masas solares y alimenta un chorro gigante. El telescopio del horizonte de sucesos capturó la primera imagen de la sombra de un agujero así, una mancha oscura sobre un flujo de acreción brillante, lo que supuso una confirmación directa del panorama general relativista. Estas observaciones registran no un agujero en la imagen, sino una sombra gravitacional, una región desde la cual la luz tiene la menor probabilidad de llegar a nosotros.
Fact number 4. Quantum field theory posits that black holes radiate on a curved background, a phenomenon called Hawking radiation. An external observer perceives the hole as having a temperature inversely proportional to its mass. Smaller black holes are hotter and larger ones are nearly cold. For an object of stellar mass, the temperature is extremely low, well below the cosmic microwave background, meaning such radiation is currently undetectable. In theory, a black hole should evaporate by shedding mass, and its lifetime scales with the cube of its mass. Supermassive black holes will endure for a time much longer than the universe's current age. The mechanism is rooted in quantum fluctuations that emerge at the event horizon. But the specifics of the information paradox, how to reconcile quantum unitarity with evaporation, remain subjects of ongoing research and debate. Fact number 5. When matter falls into a black hole, it forms a hot accretion disk. Friction and magnetic fields heat the gas to millions of degrees, causing it to emit X-ray and ultraviolet radiation. The efficiency of this gravitational power plant in turning mass into energy is incredibly high. For a black hole that spins quickly, a Kerr black hole, this efficiency can be as high as tens of %, exceeding that of nuclear fusion. Jets are formed by streams of plasma that are ejected along the axis of rotation at speeds close to the speed of light. One mechanism for this is the extraction of rotational energy through magnetic fields that are stretched by the ergosphere. The disk's brightness is limited by radiation pressure, a concept known as the Eddington limit. If the disk becomes too bright, the radiation will push the gas away, controlling the rate at which the central object is fed. Sixth point, the rotating black hole, described by the Kerr solution, has a unique zone outside its event horizon called the ergosphere. Within this ergosphere, space-time is effectively swept along by the rotation, meaning even light cannot remain still compared to distant stars and must participate in the overall vortex. This region is not the horizon. It is still possible to leave it. However, every world line within the ergosphere is required to rotate in the direction of the spin. The Penrose process utilizes this property. A particle splits in the ergosphere, with one fragment falling past the horizon carrying negative energy from the perspective of an observer at infinity, while the other fragment departs, taking with it more energy than the original particle possessed. Theoretically, vast amounts of energy can be extracted from this rotation, up to about 29% of the mass energy of an extreme black hole. This makes the ergosphere a natural, albeit very hard to access, cosmic flywheel. Fact number 7. The radius of the innermost stable circular orbit, or ISCO, establishes the inner boundary for stable, circular movements within the accretion disk. For a Schwarzschild black hole that is not spinning, the ISCO is found at 6 gm/c squared, which translates to 3 Schwarzschild radii. However, for a Kerr black hole rotating as fast as possible, with motion in the same direction as the spin, the ISCO moves extremely close to the event horizon. This shift impacts the energy generation process during accretion. The percentage of mass converted into emitted radiation increases from about 5 to 6% for the Schwarzschild case to approximately 40% theoretically for a black hole spinning very rapidly. Astronomers gauge the spin of black holes by analyzing their X-ray emissions. By observing the reflection off the inner disk and using a method called continuum fitting, they can infer that some black holes within binary systems and at the centers of galaxies are rotating with a spin parameter A star very close to 1. This finding supports the high efficiency and bright output of their accretion disks. The 8th point discusses the photon sphere surrounding a black hole. This is an orbit at a distance of 3 gm/c squared for the Schwarzschild case, where light can travel in a circle. However, any minor perturbation results in either the light escaping or falling in. The intense distortion creates what an observer observes as a gravitational shadow. Its diameter for a non-spinning hole is around 5.2 Schwarzschild radii, and for a spinning one, it's slightly warped and shifted. In reality, the shadow is bordered by a bright photon ring, rays that have circled the object many times. Doppler boosting makes one side brighter, where gas in the disk is moving toward us. This exact contrast was captured by the Event Horizon Telescope interferometers. Not a gap in light, but a region from which rays barely arrive, tangled in extreme spacetime geometry and swallowed by the horizon. Fact 9. The term spaghettification refers to a physical effect, not a figurative one, resulting from tidal forces. Specifically, the variation in gravitational attraction between one's head and feet causes elongation and compression of the body. For black holes originating from stars, this gravitational difference is so pronounced that it becomes lethal considerably before the event horizon is reached. In contrast, supermassive black holes exhibit a milder field gradient at their horizon. Consequently, an astronaut, provided they disregard radiation and magnetic disturbances, could traverse the boundary without experiencing immediate catastrophic consequences. The fatal outcome would manifest at a greater depth, near the singularity. When a complete star approaches the central black hole, the outcome can be tidal disruption. The star is ripped apart, with half of its material being expelled and the other half returning, leading to an ultraviolet X-ray emission and a characteristic decline in luminosity approximately proportional to T to the -5/3.
Such occurrences, known as tidal disruptions, have been detected on multiple occasions and function as markers for concealed massive entities.
Fact number 10. Black hole mergers create disturbances in the fabric of space-time, producing gravitational waves. These waves are tiny stretches and squeezes amounting to fractions of a proton over distances of kilometers. In 2015, the first signal from a pair of black holes identified as GW 150914 was recorded. This signal exhibited a characteristic chirp that grew in frequency and amplitude until objects with masses of several tens of suns combined into one. This merger released energy equivalent to 3 solar masses in pure form within fractions of a second. Since then, the LIGO and Virgo detectors have gathered data from dozens of similar events, and their statistical analysis indicates a range of masses and spins for these black holes. These observations provide confirmation of general relativity in strong gravitational fields and offer insights into the origins of these pairs. The possibilities include them being formed as close binary stars or meeting later in dense clusters through gravitational interactions. 11th fact. The narrative of black holes commenced much earlier than the actual term was established. In the year 1916, Karl Schwarzschild identified the first exact solution to Einstein's equations concerning a mass with spherical symmetry. In the year 1939, Oppenheimer and Snyder proved that a star's core, if it is sufficiently massive, will inevitably undergo collapse. The Chandrasekhar limit, approximately 1 4/10 of the Sun's mass, served to separate the destinies of white dwarfs and supernovae. Subsequently, the Oppenheimer-Volkoff limit, ranging from about 2 to 3 solar masses, distinguished between neutron stars and black holes. The phrase black hole was officially adopted by John Wheeler towards the end of 1969, though it had appeared in print prior to this. From that period onward, the concept transitioned from theoretical speculation. In the 1970s, Bekenstein made a link between the event horizon's area and entropy, and Hawking predicted quantum evaporation. This shift transformed black holes from being considered cold graves into objects that could be understood through thermodynamics. Gradually, the framework of concepts grew to include the ergosphere, shadow, radiation, and gravitational waves, thereby elevating the hypothesis to the status of an observable phenomenon. Fact number 12. The pursuit of black holes is accomplished through a series of ingenious indirect approaches. Within X-ray binary systems, exemplified by Cygnus X1, the hidden partner pulls gas from a nearby star. The heated accretion flow emits radiation in the hard spectrum. Astronomers ascertain the dynamic mass of the unseen object by studying the movements of the bright donor star. If this mass exceeds the established limits for neutron stars, it is deemed a strong candidate for a black hole. In galactic nuclei, masses are gauged by the speeds of stars and gas and by the effect of reverberation, which is the delayed response of wide emission lines to outbursts from the disk. The gravity interferometer tracked the star S2 on its elliptical path around the Milky Way's core and registered a gravitational redshift at pericenter, confirming a supermassive entity. The Event Horizon Telescope project linked radio telescopes across the globe to observe the shadow, first M87 star, then Sagittarius A. These are visual markers of extreme gravity, not simply gaps in light. Fact 13. A common misconception is that a black hole sucks in everything around it, destroying galaxies. In reality, its gravity follows the same laws. At distant orbits, it behaves like ordinary mass, and planets or stars can orbit stably if they do not cross the region where stability is lost. Another popular fear concerns many holes from colliders. However, cosmic rays with energies higher than accelerator energies have been bombarding Earth and stars for billions of years. If such microscopic objects were born and survived, we would see their effects. Furthermore, the theory suggests that the hypothesized tiny holes evaporate through Hawking radiation extremely quickly. The myth that everything will eventually fall into a hole is also incorrect. The evolution of the universe includes expansion, baryon decay is questionable, and there is the thermodynamics of dark energy. There are many scenarios, and an all-consuming finale is neither the only one nor proven. Black hole records are striking due to their immense scale and high speeds. Supermassive black holes observed in quasars from the early universe, a mere few hundred million years post-Big Bang, had already accumulated masses of hundreds of millions of solar masses and beyond. This leads to the "how did they grow so fast" puzzle, with theories including seeds from direct gas cloud collapse, rapid growth during super-Eddington accretion phases, and frequent mergers. The M87 star giant black hole has a Schwarzschild radius spanning tens of astronomical units, which is equivalent to Pluto's orbit within our solar system. Yet, all its mass is confined to an area from which light cannot escape. At the opposite end of the spectrum are the lighter, stellar mass black holes. In binary systems, these are estimated to have masses ranging from a few to tens of solar masses. Additionally, based on spectral and relativistic indicators, the spins of some of these are approaching their maximum limits. Even dormant supermassive black holes, like our SGR-A star, occasionally show activity with flares when a random gas parcel enters their central vortex. The 15th fact is that the aesthetic of the gravitational abyss was swiftly picked up by culture. In Interstellar, the visual representation of a black hole was developed from calculations overseen by Kip Thorne. Rays were traced within curved spacetime, which meant the disk could be seen not only from its plane, but also from above, as light wraps around the hole and forms an aura. The film slightly simplified brightness differences and colors to help the audience see the details. But the fundamental idea of a photon ring and the Doppler effect from nearby gas reflects actual physics. The magnitude of time dilation on a planet near the horizon remains a debated aspect of the film. For an hour to pass as years, the conditions would need to be extreme and challenging to align with a stable orbit and the ability to survive tidal forces. Nevertheless, the film did something uncommon. It brought exact mathematics into big-screen cinema and gave viewers an image that is close to what interferometers produce today. 16th fact. The relativistic dragging of spacetime by rotation, known as the lens-Thirring effect, makes particle and gas clump orbits precess around a black hole's axis. Closer to the horizon, this causes the Bardeen-Pedersen effect. Inner disk layers align with the spin's equatorial plane, while outer layers remain tilted, forming a bent flow geometry. This bending changes jet direction and can explain smooth jet turns from astronomical units to parsecs. In X-ray systems, precession shows up as quasi-periodic oscillations, weak but steady brightness fluctuations on millisecond to second timescales. Their frequencies, which depend on mass and spin, are used as indirect clocks for strong gravity. By comparing multiple oscillation modes, researchers try to reconstruct the near-horizon region's geometry without direct imaging. Fact number 17. Black holes not only consume matter, but also shape their surroundings through a feedback mechanism. The energy generated by accretion and jets heats and expels gas, thereby slowing the process of star formation in galactic nuclei. Within the hot gas of clusters, voids are observed, which are cavitation bubbles inflated by the jets of active nuclei and illuminated by the X-ray glow of the surrounding plasma. This action against gravitational cooling helps to explain why massive elliptical galaxies are often red and dead rather than actively forming stars. The masses of central black holes correlate with the properties of the bulge, such as the dispersion of stellar velocities and luminosity, which points to their joint evolution. When a nucleus becomes active, we observe a quasar, an object with superluminosity due to high accretion, possessing broad and narrow lines and showing variability over days to years. When the fuel supply is exhausted, the nucleus shuts down, but remnants of previous energetic events such as shock fronts and chemical enrichments remain detectable in the interstellar medium for a considerable time. Fact number 18. Black holes exhibit thermodynamics. The standard laws of black hole mechanics bear a formal resemblance to conventional laws. Surface gravity serves as temperature, the area of the horizon equates to entropy, and mass is equivalent to internal energy. Bekenstein first put forward the idea that entropy is proportional to area, and Hawking calculated the specific factor. 1 bit of disorder is associated with every quarter of the area in Planck units. This yields an astonishing insight. A black hole is the most efficient information storage medium per volume. However, the manner in which this information is lost or kept during evaporation is an ongoing question, referred to as the information paradox. Current models suggest concepts like soft hair, gravitational replication effects, holography, and firewalls, but a consensus has not been reached. It is fairly acknowledged that this is a vibrant area of theoretical research, where precise mathematical outcomes and observable effects are still uncommon and demand careful understanding. The 19th fact. Accretion can be different. The classic Shakura-Sunyaev thin disk is cold, geometrically thin, and radiatively efficient, meaning almost all gravitational energy is released as light. However, when inflow rates are low, a rarefied hot flow is formed, which is radiatively inefficient, ReAF or ADAF. In this flow, energy is carried inwards and the spectrum shifts towards hard X-rays. In X-ray binaries, these modes switch places. The soft state is dominated by the disk's thermal radiation, while the hard state is dominated by a corona of hot electrons that scatter soft photons via Compton scattering. These transitions are accompanied by the activation or weakening of compact jets, which shows the connection between the disk, corona, and jets. A fundamental plane of activity has been observed. The mass, X-ray luminosity, and radioluminosity of objects, from stellar to supermassive, fit into a single scaling law, underscoring the universality of accretion physics. Fact 20. Primordial black holes are hypothetical objects that could have formed not from stars but from high-density fluctuations in the early universe. Their masses might have ranged from asteroid-sized to stellar and above. In recent years, the possibility that such objects could form a significant part of dark matter or explain some gravitational wave sources has been discussed. However, strict limits apply. Stellar microlensing, gamma-ray background from small hole evaporation, star cluster dynamics, and cosmological data all constrain the allowed mass ranges. Observational evidence has not yet yielded a clear answer, and the scenario remains a subject of debate. It's possible that some LIGO-Virgo events are related to primordial holes or entirely to the stellar channel. It is accurate to describe this as a compelling idea at the confluence of cosmology and astrophysics that is still awaiting decisive tests. Fact 21. Gravitational lensing is an unobtrusive sign of a black hole, occurring when its field warps the light from a distant star or galaxy. Strong lensing can produce an Einstein ring or break a source into arcs, but for single stellar mass objects, more subtle effects are commonly observed. A short-lived increase in brightness, microlensing, and a minuscule shift in the visible position of the background, an astrometric signature in billionths of an arcsecond. This is how telescopes like Hubble and Gaia have recently announced candidates for solitary black holes. The light from distant stars behaved for days and months as if an invisible mass of several solar masses was pulling it. The method is important because it does not require accretion or X-rays. It allows us to see dim objects that would otherwise be completely hidden, presenting a rare chance to measure the mass of the galaxy's unseen gravitational frameworks. Fact 22. The no-hair theorem posits that a stationary, isolated black hole in general relativity is fully defined by three parameters: mass, spin, and electric charge. In astrophysical reality, the electric charge is swiftly neutralized by the surrounding plasma, leaving only mass and spin. This implies a strict predictability for the post-merger state. The resulting new hole should emit a set of quasi-normal modes, like a space-time Bell's ring with precisely calculable frequencies and damping. Gravitational wave detectors are attempting to catch these overtones to conduct black hole spectroscopy and test Kerr geometry, checking if the observed notes match the strict theoretical ones. While current errors are substantial, the initial indications are consistent with the theory. Any stable deviations would be sensational, suggesting either the actual existence of hair at the horizon or the need for new physics beyond general relativity. Fact 23. Magnetic fields serve as the underlying structure for accretion machinery. By analyzing the polarization of light using event horizon interferometers, ordered patterns have been identified in the vicinity of M87's shadow. These fields are configured in a twisted manner, akin to hoops and spokes, which channel plasma towards the poles. This configuration allows for the operation of a mad regime. In this scenario, the incoming plasma stream delivers a significant magnetic flux that resists further accretion onto the black hole, while simultaneously fueling the jet. The Blandford-Znaiec mechanism extracts rotational energy from the black hole through these magnetic fields, operating like a large-scale electromagnetic generator. The correlations observed between radioluminosity, polarization, and jet power lend support to this explanation. A more abundant magnetic reservoir and a higher spin rate contribute to a more stable and brighter jet, which can traverse interstellar space for thousands of light-years. Fact 24. Intermediate mass black holes are the connecting piece between stellar and supermassive black holes, having masses from hundreds to hundreds of thousands of solar masses. Their existence makes sense for scenarios describing the growth of galactic giants, but there are few and unclear observations. Candidates show up as very bright X-ray sources at the edges of galaxies, where typical accretion has trouble reaching such brightness without extra mass. There are also movement hints in dense globular clusters. Stars move as if a heavy, unseen mass is in the center. Gravitational wave events with resulting masses of about 100 solar masses also suggest hierarchical mergers, when holes are created, merge, and then form pairs again. Right now, it's a puzzle of indirect proofs, but if intermediate mass black holes are confirmed, they will become the natural starting points for early quasars. Fact number 25. The universe's long song, according to modern data, includes a background of nanohertz gravitational waves. This is an ultra-low frequency hum. Interpretations suggest it is produced by populations of supermassive black hole pairs within galaxies that are merging. Laser interferometers cannot capture these waves due to their excessively low frequencies. Instead, millisecond pulsars, acting as highly accurate beacons, serve as the clocks. When the fabric of space-time gently undulates, the arrival times of the pulses drift in unison across the sky. International pulsar timing projects have reported statistical indications of such a background. The signal possesses the correct angular correlation and a spectrum that aligns with expectations from a vast array of galactic cores in various stages of spiral convergence. This is not a singular loud event as observed by LIGO, but rather the cumulative subtle rustling of a billion distant dances, offering a clue to the evolutionary history of galaxies and their central massive black holes. Fact 26. Upon the coalescence of two black holes, gravitational waves carry away both energy and momentum. Should the radiation be asymmetrical due to variations in mass or spin orientation, the newly formed black hole receives a directed force referred to as a gravitational kick. Based on calculations and modeling, this kick can propel the object at speeds of thousands of kilometers per second, though velocities in the hundreds of kilometers per second are more typical. For supermassive black holes located at the cores of galaxies, this is a critical factor, as such speeds can rival gravitational forces, enabling the object to migrate from the nucleus or even be ejected into the galactic halo. Astronomers are engaged in identifying displaced active nuclei, asymmetrical emission lines, and quasars exhibiting noticeable shifts in relation to the stellar center, which may serve as evidence of these kicks. The phase preceding the collision itself leaves other indicators. A binary black hole can expel stars, resulting in shattered nuclei. Post-kick, it might take along a dense stellar grouping, a hypercompact cluster gravitationally bound to the departing entity. The 27th fact. A black hole's intake in a calm galaxy is marked by infrequent tidal shredding of stars. It is estimated that in a typical galaxy, such an occurrence takes place about once every 10,000 to 100,000 years. This happens when a star gets too near, is torn apart by tidal forces, with some of its matter going off and some falling back, resulting in a flash with a characteristic dimming of brightness as T to the power of -5/3. There are jetted occurrences, where a narrow stream is switched on and the signal penetrates the gamma and X-ray spectrum. There are optically thick ones, where the majority of energy is processed by winds and radiated in ultraviolet and optical light. An infrared echo reflection from the heated dust torus around the nucleus is often seen. Partial shredding also occurs. The star is nibbled and it returns to an extended orbit, providing periodic surges. These different modes assist in indirectly measuring the masses and rotations of hidden giants, and in studying how gas moves and loses energy close to the horizon. Fact 28. A dependable spinometer is the relativistically distorted iron kappa line. In an undisturbed atom, it is located near 6.4 keV. However, light in the sub-horizon disk is subject to gravitational redshift, Doppler broadening, and aberration. This produces an asymmetric sawtooth pattern with a blurred red wing that extends several keV. Modern X-ray observatories simultaneously measure this line and the reflection hump from 20 to 30 keV. They also capture the time delays between coronal variations and the disk's response, termed reverberation, which occur over milliseconds to hours. By comparing the line's shape, the delays, and the continuum, they simulate the inner disk edge's position, which is associated with ISCO, and thereby deduce the spin. This technique is statistically powerful but prone to systematic issues like corona geometry, disk ionization, and absorption along the path. For this reason, spin estimates are cross-checked using several independent approaches, aiming for consensus before concluding on the rapidity of a specific hole. Fact 29th. For a supermassive black hole to grow, a galaxy needs to supply a large volume of cold gas to its center and remove its angular momentum. This happens through galaxy mergers, bar-in-bar configurations, spiral instabilities, and turbulent inflows from the intergalactic medium. At the core, gas gets compressed, creating stars and feeding the disk at the same time. Dense dust and gas block some of the core's light, forming a torus. Looking along the torus's plane shows type 2, narrow lines, while looking from above shows type 1, broad lines. This unification view is made more complex by evolution. Many cores are so densely hidden, Compton thick, that their impact is only seen in hard X-rays and the cosmic X-ray background. The peak of this background is explained by the combined effect of many hidden AGNs. Activity happens in stages, a duty cycle, short bursts in cosmic terms, lasting hundreds of thousands to millions of years, with breaks where the core goes quiet. Fact 30. The upcoming era of research is characterized by multi-channel strong gravity astronomy. Next-generation radio interferometers are being developed to not only image shadows, but also to record movies of the region around Sagittarius A star, following the orbital paths of plasma clumps over minutes and hours. Large optical telescopes employing adaptive optics will persist in tracking the so-called streamer stars near the galactic center, thereby refining the understanding of the gravitational potential. X-ray spectrometers equipped with microcalorimeters will produce highly precise spectral lines and reverberation maps, facilitating the measurement of coronal altitude and the dynamics of stellar winds. A space-based gravitational wave observatory, sensitive in the millihertz frequency range, is targeting binary systems of intermediate and supermassive black holes with the aim of providing tomography of the universe of coalescing objects. Extensive sky surveys in optical and infrared light will capture numerous tidal disruption events, converting rare phenomena into statistical data sets and rendering the physics of the event horizon amenable to precise, repeatable measurements. Fact number 31. In the area around Sagittarius A star, from 2011 to 2014, a puzzling entity called G2 functioned as bait. This entity was a dense collection of dust and gas moving along a stretched orbit and passing its closest point to the central mass at a distance of several thousand Schwarzschild radii. Astronomers were looking forward to a dramatic outcome. The expectation was that some of the material would be ripped apart, heated by tidal forces, and then erupt in X-ray and radio waves, similar to a small banquet for the black hole. However, the resulting burst was rather small, as if the cloud had held its form better than a blob of gas. This introduced another idea. G2 was not just gas, but perhaps a young star or two stars that had recently merged, covered by a dusty shell that survived the close approach. The story unfolded to show that even in the hungry heart of the galaxy, food comes in pieces, and not every close flyby turns into a feast, with the dynamics near the event horizon being more complicated than simple patterns. Fact 32. EMRI refers to extreme mass ratio inspirals, where a star-sized object orbits a supermassive black hole, gradually spiraling inward over years. The gravitational waves produced by these events fall within the millihertz frequency spectrum. These waves encode a precise map of the Kerr geometry, detailing hundreds of thousands of orbits, precessions, and resonant behaviors. Projections suggest that a future space-based antenna will be able to detect these signals from galaxies far away. This will facilitate testing the concept of black hole hairlessness. Subtle variations in the signal's frequencies and phases will highlight departures from the ideal metric. EMRI originate when, in the dense stellar mix at a galactic center, an object loses energy from gravitational encounters and descends towards the core. Their signals are enduring and provide accurate data on the central black hole's masses and spins, while also shedding light on the nature of dense nuclear clusters, characterized by massive stars, black holes, and complex gravitational interactions. Fact number 33 addresses microquasars, which are close binary systems hosting a black hole. They exhibit jets that appear to travel faster than light. Yet this does not breach Einstein's speed limit for light. The phenomenon is explained by geometry. Plasma streams at almost the speed of light at a shallow angle to our view. Due to this projection, the apparent transverse speed exceeds the speed of light. GRS 1915 plus 105 and GRO J 1655-40 are classic examples of such sources. In these systems, the disk's brightness and spectrum, the X-ray corona, and the radio jet all change in a coordinated manner, like scenes in a single play. When in a flaring state, the disk's thermal contribution grows, the corona weakens, and the jet can separate, moving as plasma packets. In contrast, during the hard state, the jet is stable and the X-ray emission is of higher energy. These correlations serve as a cosmic laboratory for the disk-corona-jet connection, scalable across many mass ranges. The same physical laws that govern microquasars also successfully describe the behavior of active galactic nuclei. Fact 34th. Beyond narrow jets, black holes also discharge powerful winds. In the spectra of active nuclei and X-ray binaries, blue shifted lines of highly ionized iron are observed, with speeds up to tens of % of the speed of light. Additionally, there are warm absorbers and broad dips in the ultraviolet, known as Bal quasars, where winds carry away substantial momentum. These streams are likely launched by a blend of radiation pressure and magnetocentrifugal forces. They contend with accretion, moving energy to the nuclear scale and outward into the interstellar medium. Observations of delays and polarization point to a complex geometry. There are equatorial and polar parts, changing funnels, and a dust shield. The consequence is crucial for galaxy evolution. Winds and jets jointly manage the thermostat, stopping gas from cooling without control and becoming stars. The 35th fact. Physicists build GRMHD simulations to understand the behavior of disks and jets near the horizon. This means solving magnetohydrodynamic equations in curved spacetime, taking general relativity into account. The results show turbulent swirls, magnetic loops, and hotspots. These transfer angular momentum outwards and energy to the corona and jets. Radiation transfer is then added. Rays are tracked along geodesics, considering redshifting, Doppler effects, and gravitational focusing. This produces synthetic pictures and light curves that can be compared to radio interferometry and X-ray data. This is how concepts about magnetically stalled disks, corona height, and field structure near M87 star and SGRA star are tested. When models and observations agree, it's not just a pretty picture. It proves that the starting equations, plasma microphysics, and the chosen metric correctly describe real life near the point of no return. 36th fact. The masses of black holes formed from stars do not exhibit a continuous distribution. Theoretical predictions have long pointed to a pair instability gap. Inside the cores of massive stars, at temperatures around 1 billion Kelvin, gamma rays create electron-positron pairs. This leads to a decrease in pressure, causing the core to collapse with an explosion. If a helium core is massive enough, a star can endure a sequence of pulsations, shedding its outer layers, pulsational pair instability, and leave behind a relatively light black hole. At even higher masses, full pair instability occurs, completely destroying the star without any trace. Within this mass range for black holes born from single stars, a gap was expected. Gravitational wave observations have added to the mystery. Occasionally, systems are detected with components that seem to fall within the forbidden zone. This suggests either hierarchical mergers or special conditions of low metallicity. The conclusion? The mass distribution is a chronicle of stellar evolution and their pairings in dense clusters. Fact 37th. It is expected that our galaxy contains millions of stellar mass black holes, existing both in binary systems and as lone wanderers. While precise estimations vary, the numbers are in the range of tens of millions of objects distributed across the galactic disk and bulge. We are only able to see a small portion, a few tens to hundreds of X-ray binaries, where accretion makes the invisible object visible. The remaining ones are silent. They are identified through microlensing, a temporary increase in the brightness of a distant star when an unseen mass passes in front of it. For such events, the typical duration lasts for weeks to months. In infrequent cases, a minute shift in the star's position can be detected astrometrically, enabling the mass of the lens to be determined. This yields a dark object with solar masses and no self-luminosity. Large-scale surveys and precise astronomy are gradually revealing a catalog of these quiescent gravitational specters, allowing us to estimate their numbers, velocity distributions, and even to observe the kicks they received during their formation in supernovae. Fact number 38. Superradiance is an exotic pathway for pumping energy out of a rotating black hole. The classic example is the Zeldovich relativistic effect. A wave reflecting from a rotating absorber can be amplified by its spin. In astrophysics, realizing this directly is hard. But if light bosons, axion-like particles, exist in nature, they form atom-like levels near the hole. Through superradiance, these levels get pumped up, like a laser medium. The result is an inflated, cloudy configuration that takes angular momentum from the hole, slowing its spin, and can emit narrow-band gravitational waves for years. From the spin distribution of stellar and supermassive black holes, restrictions are already being placed on the possible masses of such particles. If they were in certain ranges, there would be fewer fast black holes. This is an example of how horizons become laboratories for physics beyond the standard model. Fact 39. Active nuclei that change visibly are a phenomenon where a quasar loses or gains broad lines in its spectrum over years and dramatically changes its luminosity. The traditional unification scheme explained variations by viewing angle, but here the object itself is changing. Observations show that sometimes dust geometry is responsible. A cloud blocks the central lamp. But in a number of cases, the key is accretion starvation or a burst. The inflow rate decreases, the thin disk moves into a hot, rare mode, and the photons that ionize the broadline region disappear. Then the process goes the other way. From the delays in the response of gas lines to continuum variability, the sizes and structure of regions are reconstructed. And from the rates and colors, the physics of transitions between states are understood, linking galactic nuclei to microquasars. These turnarounds offer a rare chance to check how the entire machine reassembles from the horizon to hundreds of light years. Fact number 40. Sagittarius A star, the supermassive black hole nearest to us, has been utilized to test general relativity in a strong field over human-relevant timescales. The star S2, which orbits elliptically in under 20 years, speeds up to several thousand kilometers per second at its closest approach and ventures into regions where relativistic corrections are significant. During its pericenter passage, a gravitational redshift was detected in its spectral lines. Subsequently, after several years, preliminary evidence of relativistic pericenter precession was found, indicating that the orbit's ellipse rotates by a small but measurable angle per orbit. These combined effects are in agreement with the predictions of the Kerr metric for the relatively undisturbed black hole at the center of the Milky Way. Future observations will focus on even closer stars and hot gas clouds, whose rapid orbital motions will allow for the minute-by-minute recording of spacetime, testing the geometry near the horizon with exceptional accuracy. Fact 41. The area of a black hole's event horizon does not decrease in classical general relativity, a principle termed the Hawking-Bekenstein second law of black hole mechanics. Upon the merger of two objects, the combined area of their horizons must increase. While gravitational waves dissipate energy, they do not permit a reduction in the horizon's entropy. This claim is subject to empirical verification. The initial phase of a gravitational wave signal allows for the estimation of the masses and spins of the merging pair, from which their horizon areas are computed. Following the merger, the parameters of the resultant black hole and its area are deduced from the characteristic ring-down sound. Early events, exemplified by the historical GW 150914, demonstrated alignment with the law within the margins of error, confirming an increase in area. This serves as a validation of both geometry and thermodynamics in intense gravitational fields, akin to a cosmic manifestation of the second law. It is important to note that the emergence of an exposed singularity would contravene this law. Consequently, such examinations provide indirect support for the cosmic censorship hypothesis, suggesting that singularities are shielded by event horizons. Fact 42nd. The insides of a rotating black hole, by Kerr's design, are elaborate. Beyond the outer horizon, there's an inner one, dubbed the Cauchy horizon. In a perfect mathematical depiction, space-time continues past it, revealing exotic zones with changed causality. Yet physics hints at fragility. Minor disturbances, like dust or light falling in, get amplified, and energy at the inner horizon technically skyrockets, mass inflation. A real black hole probably doesn't have a smooth continuation. Its inner horizon becomes a zone of a destructive curvature cascade. It's vital to recall that an outside observer sees none of this. No signal from inside crosses the outer horizon, and these effects stay purely theoretical. They are, however, crucial. The theory's predictability, global hyperbolicity, hinges on Cauchy stability, and talks of firewalls, quantum fixes, and holography often orbit these inner limits. Fact 43rd. The movement of stars by a supermassive black hole is dictated by a lost cone, the range of angular momenta where an orbit will draw an object either inside the tidal disruption radius or toward the horizon. Two-body and resonant relaxation gradually introduce stars into this cone, and occasional victims provide fuel for tidal flares. The Hills mechanism is a separate consideration. If a tight binary star enters the core, tidal forces break the pair, the whole captures one part into a close orbit, and the other is thrown out at hypervelocity, thousands of kilometers per second. Such escapees have been found in the Milky Way's halo, and their paths lead to the galaxy center. The S-star family also lives there. Young, fast, on stretched orbits likely formed in the disk or brought by dynamic actions. The totality of these events is a record of gravity's silent hunt near the central entity. The 44th fact addresses the source of black hole pairs detected by our instruments. There are multiple ways these form. One is through the isolated evolution of a large binary star system. As it passes through a shared envelope, the stars get closer. When a star has low metallicity, its stellar winds are weaker. This leaves behind more massive cores and can align their spins. The outcome is mergers where the rotations are mostly in sync. Another way is dynamic. In dense star clusters like globular or nuclear clusters, gravity causes individual stars to meet and form pairs, pushing out smaller stars. Here, the spins are often mixed up and sequential mergers can happen, creating stars with masses that are unusual for single stars. A third idea involves the disks around active galactic nuclei. Stars migrate within the gas, get caught in pressure traps, their orbits line up with the disk, and they grow bigger by gathering material. By looking at observations like how eccentric their orbits are, their masses, how much their light has shifted to red, and especially the angles between their spins and orbits, scientists can gradually figure out how much each of these formation methods contributes. Fact 45th. To account for quasars in the early universe, seeds of supermassive black holes are necessary, having had time to grow over a few 100 million years. One proposed scenario is direct collapse. Within halos at atomic cooling temperatures, where the formation of molecular hydrogen is inhibited, for instance due to a strong Lyman-Werner background, gas bypasses stellar fragmentation and collapses as a single unit, giving rise to a supermassive star with a mass of 10 to the 4th to 10 to the 5th solar masses, followed by a quasi-star with a black center. Another scenario considers the remnants of the first stars, population 3, possessing masses in the order of hundreds of solar masses, which, under favorable circumstances, experience super-Eddington growth and evolve through mergers. An additional pathway involves sequential collisions within extremely dense young clusters, leading to the accumulation of intermediate masses. Verification efforts are underway across several domains. examining the luminosity and spectral lines of the most remote quasars, analyzing their abundance statistics, identifying indicators of active galactic nuclei in galaxies at significant redshifts, and detecting indirect evidence of feedback mechanisms that impact the ionization and metallization of the early intergalactic medium. Fact 46. The two black holes most frequently discussed, M87 star and Sagittarius A star, exhibit similar shadows but operate at distinct temporal rates. The characteristic gravity time, defined as Tg equals gm by c cubed, for SGR A star is approximately 20 seconds. An orbit along its inner stable circle lasts for tens of Tg, which translates to minutes. In contrast, for M87 star, the Tg value is in hours, and a complete orbital period spans weeks. As a result, lengthy interferometric exposures capturing the event horizon tend to average out the dynamic processes surrounding M87. However, these same long exposures blur the rapid transformations occurring at SGRA, as hot patches and outflows have time to reorganize themselves during the observation duration. A further complication when observing the galactic center is interstellar scattering. Electrons situated along the line of sight degrade the radio image, necessitating compensatory measures. To maintain image contrast, closure phases and polarization are employed. These techniques have confirmed that the magnetic fields of both objects are ordered and that their accretion flow is rotating. Nevertheless, at SGRA, photons undergo changes more rapidly than our current methods can document their trajectory. Fact number 47. In certain galactic cores that appear quiet, quasi-periodic eruptions have been found in soft X-rays. These bursts repeat every few hours or days, increase in minutes, and then quickly decrease, amplifying brightness by several to tens of times. Radio support is generally faint, implying the jet has a secondary role, with the inner disk and corona being the main contributors. The masses of the central holes in these systems are estimated at 100,000 to 1 million solar masses, which produces typical light scales that agree with observed delays. Explanations are in competition: partial tidal biting of a star on an eccentric orbit, localized thermal instabilities in the disk, or periodic gas dripping from the wind. The period stability is initially surprising, then it starts to drift, as if the orbit or feeding pattern is slowly changing. There is no agreement, but QPEs themselves have opened a new view into the physics of thin accretion layers near small supermassive black holes. Fact number 48 explains that X-ray reverberation, which are echoes lasting from seconds to hours between the corona and the disk, has become a method to measure the geometry of the region close to the event horizon. In a setup resembling a lamppost, a compact corona located above a pole shines light downwards. Some of these photons are reflected by the disk, producing an iron line and a hump at energies of tens of keV. Changes in the original continuum are observed first, while the reflected signals arrive later, with a time delay of about a few gm by c cubed. This corresponds to milliseconds in microquasars and minutes to hours in active galactic nuclei. These time lags, along with the line profiles, allow for the estimation of the corona's height, often less than 10 gravitational radii, the degree of disk ionization, and can even reveal the bending of light predicted by general relativity. Scaling these lags with mass provides an independent estimate of the black hole's mass, supplementing the established optical reverb mapping technique using broad lines. In essence, this leads to a rare accomplishment, nearly geodesic tomography of spacetime derived from light delays. Fact number 49 states that the metal content of a star that forms a black hole greatly impacts the black hole's mass. When a star has fewer heavy elements, its winds that move in a straight line are weaker, and it loses less mass before it collapses. This means it ends up with heavier cores and therefore heavier black holes. In binary star systems that are close together and spin quickly, a chemically homogeneous evolution can take place. This is because mixing stops the star from getting bigger, it doesn't go through destructive stages, and the pair stays close, which is important for two heavy black holes to merge later. If there's a fallback when a supernova happens, it causes small kicks when the system is born, making it more likely to survive. Statistics from gravitational waves suggest that bigger events are found more often at greater redshifts, where the average metal content is lower. This adds to the understanding of how the early universe had fewer heavy elements. However, direct proof of this cause and effect isn't available, so scientists are cautious in their conclusions by combining models of stars, how binary systems behave, and what they observe. The 50th fact. Binary supermassive black holes are expected consequences of galaxy mergers, but observing them at sub-parsec distances is hard. At kiloparsec distances, two active nuclei are directly seen. Closer, indirect signs are looked for: quasar light timing, double or drifting broad line peaks, and S-shaped jet curves. Many of these signals have been found to be rare noise, cloud movements, or disk effects, so the community treats candidates strictly. Theory long discussed the final parsec, how a pair would shed orbital momentum when stars nearby are already mowed down. Solutions are three-dimensional, not spherical, gravity, gas disks with torques, and massive disturbers. The nanohertz gravitational wave background, noticed from pulsar timing, is exactly expected from a collection of such pairs. It won't point to one guilty party, but will confirm that for billions of years, the universe has been full of a choir of slow, tight dances of black hearts. Fact 51. X-ray polarimetry has provided a new approach to the geometry of zones near the horizon. While spectra and delays inform about what and when, the polarization vector's direction indicates where and how fields and rays are aligned. Modern instruments have made initial measurements of polarization fraction and angle in black hole binary systems and active nuclei. A moderate but steady polarization is found in the hard state. When moving to the soft state, the angle shifts, implying the corona is either descending towards the disk or extending into a jet space. The reflected component, tied to the iron line, is polarized differently, allowing the separation of corona and disk influences by their fingerprints. By correlating polarization phase rotations with quasi-periodic oscillations, researchers determine the photon's source's height and the degree of trajectory bending from general relativity. This is a rare case where a single light curve allows the extraction of a three-dimensional image that is not directly visible. The 52nd fact. The ultimate test for general relativity is a pulsar in a close orbit around Sagittarius A star. Its pulses serve as signals from atomic clocks sensitive to time dilation, precession, and the Shapiro effect. However, radio waves in the galactic center scattered due to turbulent plasma, blurring their rapid rhythm. In 2013, a magnetar, a rare relative of a pulsar, was found near SGR-A. Its signals helped measure the scattering extent and the magnetic environment along the line of sight. It was determined that the fog was less than initially feared, meaning the opportunity to find regular pulsars persists. If a millisecond pulsar, acting as a synchronized beacon on an orbit spanning months to years, can be captured, its timing will provide mass with unmatched precision, measure spin, and even the central object's quadrupolar moment, a direct check of the Kerr metric's hairlessness. At present, this is a task for deep surveys on frequencies with weaker scattering and requires patience. The search is akin to fishing in a noisy river, but the catch is worth the effort. Fact number 53. Black holes and dark matter are theoretically found at the event horizon and in galactic cores. If a supermassive black hole developed slowly within an existing halo, calculations indicate a spike, a dense gathering of dark matter nearby, which could strengthen signals from potential annihilation. In actual galaxies, stellar bars, tidal forces, and mergers can diffuse this profile, meaning direct proof is absent. Gamma-ray observations of the Milky Way's center yield mixed clues and strict limitations. Conversely, dark matter could affect black hole growth by delivering more mass to the nucleus and altering star cluster dynamics. This effect is subtle and relies on models. It is proper to state that the interaction of black holes with dark matter is a lively research area. Observational data is narrowing down the parameter space, but a definitive picture is not yet formed. Any claims about detecting spikes need caution and verification by independent telescopes and methods. The 54th fact highlights that flares from black hole binary systems draw a characteristic hysteresis loop on the hardness-intensity diagram. The object starts from a quiet state, increasing its brightness in the hard spectrum with a dominant hot corona and a stable, compact jet. Once a threshold is reached, the system moves to a soft state. The thin disk heats up, the hard component weakens, the jet fades, and sometimes single plasma bullets are fired. When brightness drops, the reverse transition happens at a different luminosity, creating the loop due to asymmetric physics. Explanations involve the evaporation-condensation of the inner disk, changes in corona height, and magnetic flux. This cycle takes weeks to months, but scales up. In active galactic nuclei, similar transitions last years to decades and explain quasars' changing looks. Hysteresis is more than a visual pattern. It's a map of regimes linking the disk, corona, and jet into one machine. Fact 55th. Water can act as a laser for an astrophysicist. Within the nuclei of some galaxies, H2O molecules in the dense, warm disk regions emit a megamaser, a strong microwave emission at 22 GHz. In NGC 4258, these beacons are positioned along an almost perfect Keplerian disk. This configuration allowed for the measurement of the central black hole's mass and the geometric distance with exceptional accuracy. Velocity was derived from frequency shift, radii from angular position, and accelerations from their variations. The result is pure Newtonian mechanics near the horizon, free from complex luminosity assumptions. Such systems are infrequent but highly prized. They calibrate the universe's distance ladder, refine the Hubble constant, and provide a means to weigh black holes in the intermediate mass range. In environments where dust obscures optical views, radiomasers map the disk with billionths of a second precision, revealing gas orbiting in the last tens of thousands of gravitational radii before the point of no return. Fact number 56. Radio galaxies, characterized by an X-shaped morphology, are visual chronicles of sudden shifts in jet paths. The captured images display two sets of lobes. One is active and slender, piercing through the intergalactic gas, and the other comprises pale wings that extend at a right angle. The spectral age of these wings is generally longer, signifying that their electrons have aged. This indicates that the flow once proceeded in that direction, but the axis subsequently underwent a rearrangement. Multiple mechanisms are suggested for this phenomenon. A rapid flip of the supermassive black hole spin following a merger with another black hole can result in the jets changing direction almost instantaneously. A more gradual process involves the internal disk aligning itself with the spin plane, following the Bardeen-Pedersen principle. The jet's axis gradually moves, leaving behind curved marks. There is also the backflow theory, postulating that plasma from the primary lobes returns and spreads sideways, forming the wings. Low-frequency observational surveys, like those performed by LOFAR, are uncovering more of these remnants. Through examining their symmetry and the times it takes for them to cool, it is possible to estimate over how many millions of years the core experienced these switching events, thereby providing brief insights into the history of mergers and directional changes of the central entity. Fact 57. Narrow-line Seyfert 1 galaxies, NLS-1, are essentially small-scale versions of quasars. Their central black holes possess masses typically between 1 million and 10 million times the mass of our Sun, and they radiate at a significant fraction of the Eddington luminosity. Spectroscopically, they are characterized by a strong presence of Fe2, a narrow H-beta emission line, and a common soft excess feature in their X-ray spectra. For an extended period, the prevailing view was that powerful relativistic jets were a phenomenon confined to the most massive galactic cores. However, the advent of gamma-ray observatories brought to light the existence of jetted NLS-1. Some of these objects demonstrate fluctuations and bursts of energy at high frequencies, mirroring the behavior of mini-blazars. This observation implies that the accretion disk can enter a slim phase when the rate of matter falling onto the black hole surpasses the Eddington limit. In this slim disk scenario, emitted radiation is partially confined and transported by the outflowing matter, and magnetic fields are capable of forming a jet even when the central black hole is not exceptionally massive. A point of caution is that mass determinations made using the widths of spectral lines in such objects might be less accurate, potentially underestimating the true mass due to factors like viewing geometry and the pressure exerted by radiation. Despite these considerations, the fundamental takeaway is that the processes responsible for initiating jets operate under a more diverse set of circumstances than what was accounted for in earlier, more restrictive unification schemes. Fact 58. Black holes are central to multi-wavelength astronomy and neutrino physics. When a blazar, a jet aimed almost directly at us, flares, it can produce not only photons but also high-energy neutrinos from its interior. In one significant event, a high-energy neutrino from an Antarctic detector aligned in sky location and time with an active blazar, and ground-based gamma-ray telescopes recorded a simultaneous flare. This interpretation supports hadronic scenarios, where protons within the jet collide with photons, generating pions that subsequently decay into neutrinos and gamma rays. However, the statistical evidence is currently limited, and not all similar associations are verified due to substantial background interference and random variability. Nevertheless, this possibility directly links black holes to the production of cosmic rays with energies reaching peta-electron volts and beyond. Radio galaxies like the nearby Centaurus A and blazars featuring powerful jets remain the main suspects, with each multi-channel outburst acting as a crucial test for models describing particle acceleration near the event horizon and within the jets. The 59th fact is that polarization in the sub-millimeter and millimeter ranges has acted as a compass for mapping magnetic fields at the horizon. Interferometry of M87 star revealed more than just a shadow. It showed a map of polarization vectors arranged like hoops and spokes, suggesting a powerful toroidal field that stabilizes the jet space. For Sagittarius A star, the measured Faraday rotation measure, which is the plasma's effect on the polarization plane, is substantial. This points to a hot, ionized environment near the black hole and imposes an upper limit on the accretion rate. Excessive gas inflow would cause depolarization, which would obscure the signal. Current estimates indicate that the inflow rate to the galactic center is very low, significantly less than the Sun's mass per million years. This accounts for its starved state and infrequent bursts of activity. When polarization maps are correlated with GRMHD models, the conclusion is strengthened. The magnetic flux at the horizon is considerable, and the disks frequently operate in a magnetically stalled mode, where the jet draws energy from the black hole's rotation. Fact 60. The quest for binary supermassive black holes often utilizes periodicity in quasar light, but nature is cunning. Accretion red noise can easily mimic cycles. Still, a few systems maintain focus. In one system, the optical light curve for years presented an almost sinusoidal pattern with a period of several years, as if the pair's orbit was changing Doppler boosting. Another, a renowned blazar with a century-long history of flares, displays quasi-periodic double peaks, which are interpreted as the secondary companion impacting the primary's disk during pericenter passage on a highly inclined orbit. Spectra sometimes show split broadline peaks, suggesting two moving sources. And parsec-scale radio jets bend in an S-shape, as if the axis is precessing. Each of these hints is unreliable on its own, but together with the nanohertz gravitational wave background, they depict a consistent scenario. Binary nuclei do exist, but catching them in the act before the final merger is hard. Fact number 61 discusses the Eddington limit, which functions as a light ceiling for accretion processes. This limit is reached when the pressure exerted by radiation scattered by electrons equals the force of gravity, thereby stopping the free fall of gas. The established formula indicates a characteristic luminosity of L-ed approximately 1.3 times 1038 m divided by m sol ergs for plasma exhibiting Thomson scattering. However, natural phenomena often deviate from this. One such deviation is beaming, where radiation is emitted in a focused, narrow beam. This allows the local radiation flux to exceed the average limit without triggering a disk disruption. Another factor, present during high accretion rates, is the slim disk configuration. In this setup, energy is trapped by photons and transported inward via advection at a rate exceeding outward escape, while the disk's increased geometric thickness offers self-shielding. The outcome is that episodes exceeding the Eddington limit are indeed observed. Ultra-luminous X-ray sources and some Seyfert galaxies are believed to operate under these conditions, expelling excess momentum through winds. Therefore, the Eddington limit remains a useful benchmark, not an absolute restriction, as it can be circumvented by manipulating the flow's geometry, energy transfer mechanisms, and magnetic structure. The 62nd fact states that black hole mergers produce more than just a chirp and diminishing overtones in spacetime. They also leave a subtle, lasting imprint called gravitational memory. When momentum is carried off by gravitational waves, observers at a great distance observe a singular shift in the metric. Specifically, two test masses that were vibrating in unison are found to be minutely displaced after the wave's leading edge has passed. This phenomenon includes both linear and nonlinear Christodoulou memory components. For individual events within LIGO's detection range, both components are exceedingly small. Nevertheless, the aggregate effect from billions of distant mergers results in a gradual, creeping displacement. Millisecond pulsar timing is particularly adept at detecting this slow shift, as pulsar timing aims to identify such correlated celestial trends. For terrestrial detectors, gravitational memory presents a difficulty, requiring either exceptionally rare, very strong, and nearby events, or intricate processing of a large volume of signals to discern the faint step-like tail that emerges after the newly formed black hole's initial ringing. Fact 63rd. A black hole's magnetosphere isn't empty. It's a rotating electromagnetic system. Its fast spin and the bending of spacetime generate electric fields. A small amount of plasma is enough to close electric currents and achieve a state close to massless or force-free. The plasma's origin is a puzzle, as the horizon itself is cold. It comes from electron-positron pair cascades. Gamma rays from accelerated particles due to curvature, plus photon-photon interactions with the disk's UV X-ray light, create these pairs. They fill gaps where the field isn't shielded fast enough. Within the magnetosphere are light surfaces, where co-rotation would hit light speed. Open field lines exit through these, drawing out a relativistic outflow that forms the base of a jet. Currents loop through the disk and corona, creating huge voltage differences. The Blandford-Zeineck mechanism extracts rotational energy, making the black hole a cosmic generator that powers the jet and wins. Fact 64. Radio galaxies are categorized into two Fanaroff-Riley families. FRI type are characterized as edge dark. Their jets lose their focused shape over distance, breaking into clumps and cocoons, with their brightness decreasing towards their tips. This is typically observed in cases of moderate power and denser surroundings, where the outflow captures nearby gas and slows down. FR2 type are known as edge-bright. They exhibit narrow, straight jets that collide with intergalactic gas, forming bright spots at the ends of their lobes. These have higher power outputs and travel through a clearer medium. The distinction between these types is approximate and can shift based on mass and the surrounding environment, but it points to underlying physics. Different feeding and magnetic flux regimes near the horizon, varying density of the surroundings, and the speed at which matter is drawn in. This is mirrored in the spectra of the nuclei as LIRG/HERG, low and high excitation radio galaxies, comparable to the hard and soft states of microquasars. This leads to a scalable understanding. The same fundamental disk corona jet engine operates on megaparsec scales, with differing environmental aerodynamics playing a role. 65th fact. If the Sun were miraculously exchanged for a black hole of the same mass, the planets would not be drawn into the abyss. Their orbits and revolution periods would remain unchanged, as gravity at a distance is identical. However, everything else would be different. After more than 8 minutes, Earth would be engulfed in night, photosynthesis would cease, and the climate would begin to cool down. Within days to weeks, the average temperature would drop significantly below zero. Oceans would start to freeze from the top, but the warm deep waters and geothermal flux, 0.1 watts per meter squared, would keep liquid water under the ice shelf for a long time. Volcanism and tidal heating, minimal for us, would become local sanctuaries. The solar wind would disappear, reorganizing space weather, and auroras would become less frequent. There would be no vacuum cleaner effect, nor an immediate collapse of celestial mechanics. The main lamp in the sky would simply go out, and an invisible, relatively quiet object would remain at the center of the solar system, which in normal conditions receives almost no fuel for accretion and therefore does not shine. The 66th fact. The galaxy's core retains memories of recent Sagittarius A-star flares through light echoes on molecular clouds. Decades to centuries ago, the supermassive black hole was more vigorously fed by gas. Its harsh radiation hit nearby clouds, causing iron to emit a fluorescent line at approximately 6.4 keV. Now, long after the flare has passed, we see the illumination as if it were running through the cloud. Bright spots appear and vanish over the years, much like a spotlight moving across an uneven surface. This shift cannot be explained by the cloud's internal mechanisms. It is a record of the nucleus's brief past activity. By measuring the rate and amplitude of the echoes, researchers can gauge the strength of the old flare and pinpoint the cloud's location on a 3D map of the center. This builds a history. SGRA is quiet now, but a century ago, it likely briefly shone like a mini active nucleus. Fact 67. In the year 2020, the Nobel Prize in Physics was split between black hole theory and observations. Roger Penrose earned the prize for his strict proof that black hole formation is an unavoidable result of general relativity given sufficiently general collapse conditions. Reinhard Genzel and Andrea Ghez were awarded for identifying a supermassive compact object at the Milky Way's center. Their teams tracked the orbits of S-stars around Sagittarius A-star for decades, measuring their accelerations, paracenters, and precession with incredible precision. The physical reality of their discovery is that the observed mass is packed into a space where only a black hole could stably exist. This link between equations and the heavens showed how Penrose's rigorous math and telescope's faint diffraction patterns coalesce into one view of the gravitational chasm at our galaxy's heart. Fact number 68. Even the most humble galaxies can conceal black holes. In dwarf systems, active cores are found with masses estimated at hundreds of thousands of suns and lower. Galaxies without a bright bulge but which still exhibit central variability and narrow lines are an example. Sometimes water megamasers are observed, suggesting a compact Keplerian disk. These micronuclei are important as direct hints about the origin of supermassive entities. If small holes are present in dwarf galaxies, it implies that their initial seeds might have been numerous and dispersed across the young universe. Another type is wandering black holes. These are the remains of ripped satellite galaxies or the products of gravitational kicks that moved them away from their centers. They now meander through halos, occasionally lighting up as insignificant off-center active regions. The search for these wanderers is carried out by examining displaced nuclei, asymmetries in lines, and X-ray points situated beyond stellar centers. Fact 69th. Ultraluminous X-ray sources are defined as objects situated beyond galactic nuclei exhibiting luminosities that exceed the Eddington limit applicable to a typical star. For an extended duration, these were largely presumed to be intermediate mass black holes. Nevertheless, subsequent observational periods have led to the discovery of a pulsar nature in some ULXs. This was evidenced by the detection of stable pulsations within their emitted light, a clear indication of a rotating neutron star core possessing a magnetic field. Consequently, fluxes surpassing the Eddington limit are not solely attributable to black holes. Mechanisms such as geometric collimation, the presence of magnetic channels, and photon traps empower neutron stars to achieve luminosities many times greater than the established classical limit. This finding does not invalidate the existence of potential intermediate black holes, but it does underscore the need for prudence. High luminosity, in isolation, does not serve as definitive evidence of mass. Accurate classification necessitates the analysis of spectra, pulsations, cyclopic lines, and the orbital dynamics of optical donor stars, a holistic collection of features essential for distinguishing a vigorous accretion state from objects characterized by significant gravitational influence. Fact 70. Discussions on the demography of compact objects include mass gaps. The lower gap exists between the most massive neutron stars and the least massive black holes. For a considerable time, black holes weighing less than about 5 solar masses were not detected in X-ray binaries, leading to the idea of a forbidden zone. Gravitational waves have provided additional context. In one recorded event, the secondary component was observed to have a mass of approximately 2 to 3 solar masses, presenting a scenario of either a record-heavy neutron star or an unusually light black hole. The upper gap is linked to the pair instability evolution of supermassive stars. Single stars that are progenitors do not leave behind black holes within a specific mass range, but hierarchical mergers within star clusters can fine-tune masses to fall precisely into the forbidden corridor. Ultimately, these voids are not rigid boundaries, but rather narrow passages within a complex network of formation channels, where stellar statistics and physics are intricately connected with the dynamics of close encounters. Fact 71. The theories of Hawking concerning quantum evaporation are examined in labs, not on actual gravitational holes, but on their equivalents known as artificial horizons. In superfluid Bose-Einstein condensates, a zone is generated where sound cannot exit against the flow. Optical waveguides and photonic crystals are employed to simulate a moving boundary of the refractive index, functioning as a horizon for light. These setups reveal correlated pairs of quasiparticles, which are either acoustic or optical, on both sides of this boundary, consistent with the predicted mechanism for pair creation at the horizon. These Hawking sparks provide strong evidence for the principle itself, yet they do not prove the evaporation of astrophysical black holes. The distinction is that gravity and the warping of space are active in astrophysical black holes, whereas an effective medium with a similar metric is utilized here. It is important to note the difference. The experiments back the general concept of quantum pair generation at a horizon, but their direct application to cosmic-scale masses needs to be done with prudence. Fact 72nd. Discussions concerning the nature of compact dark objects explore alternatives to the Kerr black hole notion, such as boson stars, gravastars, formations with exotic fields, or even wormholes. A key shared trait is the absence of a true event horizon. This absence allows light and gravitational waves to reflect partially, producing an echo following the main merger sound. The appearance of the shadow's image would change in its edge and contrast, and its spectral lines would show a different reflection pattern. Data from interferometry of the shadows of M87 star and SGRA, along with the ring-down Bell equations for gravitational waves, indicate that the conventional Kerr metric still aligns well with observations. However, the possibility of exotic models remains viable due to weak signals, considerable systematic errors, and the flexibility of these alternative theories. It is accurate to say, at present, no definitive deviations from the Kerr description have been found. But the search for echoes and subtle effects continues, as these are the specific indicators that would distinguish a horizon from a reflective skin. 73rd fact. In the near-infrared spectrum of Sagittarius A star, hotspots intermittently emerge. These are concentrated plasma blobs heated in the corona above the disk. Long baseline interferometry detected one such spot circling the black hole multiple times within a span of about tens of minutes. The light's polarization vector also smoothly turned, as if observing an orbit in a strong field with winding magnetic lines. The period and amplitude match movement at radii of just a few gravitational radii, distances where relativistic effects like Doppler boosting, aberration, and gravitational redshift are dominant. These flares, though small in energy and short-lived, are priceless as a timer at the horizon. Their rhythm and polarization turns help estimate spin, disk tilt, and magnetic field structure, bypassing the need to await rare, large accretion feasts. Fact 74th. The M87 jet is a key case study for relativistic plasma aerodynamics. From tens to hundreds of thousands of gravitational radii, its width profile is nearly parabolic, widening gradually. This indicates magnetic collimation and external pressure. Further along, it becomes more cone-shaped as pressure decreases and flow becomes inertial. Edge brightening is visible in images, bright sides suggesting a speed difference between a fast inner part and a slower outer layer. This helps maintain collimation and accelerate particles. Polarization and brightness at the jet's base fit a magnetically arrested disk model. Large magnetic flux reaches the horizon, and the black hole's spin energy is extracted electromagnetically. Choke points or recollimation shocks along the jet cause local flares and structure it over parsecs, showing how microphysics at the horizon scales into large cosmic structures. 75th fact. The subsequent generation of ground-based listeners for gravitational waves, characterized by arms stretching from kilometers to tens of kilometers, is targeting black hole spectroscopy. Their sensitivity will permit not only the confident capture of the primary ring-down post-merger, but also the registration of individual overtones, thereby enabling the verification of no hair through multiple frequencies simultaneously. For cosmology, this implies a merger map reaching deep into redshift and direct standard siren distance measurements. For astrophysics, it signifies statistics on spins and masses, including intermediate black holes produced in dense clusters. In parallel, a space-based millihertz antenna will detect the in-spiral of massive pairs years before their merger, and pulsar timing will refine the background from supermassive nuclei. Although pure black hole mergers are electromagnetically dark, hints may emerge as flares from disturbed gas in active galactic nuclei disks. Combined observations will present a rare opportunity to link event horizon geometry, plasma, and galaxy growth into one testable narrative. Fact 76th. The cooling flow problem in galaxy clusters was once thought to lead to significant star creation. The expectation was that hot intergalactic gas in cluster centers would cool quickly and settle into the core regions. However, observations showed that star formation was minimal and the gas stayed hot. It was determined that supermassive black holes play a role as thermostats. Their jets create cavities, known as bubbles, in the X-ray emitting gas. The enthalpy of these bubbles, roughly 4 PV, balances energy lost via radiation. The bubbles rise, transporting cold filaments and mixing the environment. Faint shock fronts and sound ripples, akin to those in Perseus, are visible along their paths. The cycle is completed when the central gas cools too much, causing droplets to form, chaotic cold accretion, and fall toward the black hole, increasing its feeding and heating. This feedback operates over tens of millions of years, providing a mild but constant heating that stops clusters from undergoing a snowstorm of star formation. The 77th fact states that variability is a key feature of accretion, and this feature scales with black holes. Their X-ray light curves are comparable to red noise. The strength of fluctuations increases over longer timescales but is interrupted at a particular frequency. This break frequency systematically varies with mass and the specific rate of accretion, establishing a variability plane in conjunction with these factors. Smaller and less massive black holes flicker more rapidly, while larger and more massive ones do so at a slower pace. An additional characteristic is the RMS flux relationship. The brighter the system appears at a given moment, the larger the relative fluctuations become, as if the variations are amplified during their inward journey. The propagating disturbances model accounts for this. Irregularities in viscosity and the supply of matter originate at larger radii, and as they drift inward, they alter the light emitted by the corona and disk. Delays are often observed in optical and ultraviolet light following X-ray emissions, representing the response of the outer layers to heating. Conversely, a slow optical pulse may lead, implying that the excitation originated from deeper regions of the disk. 88th fact. Black hole outbursts are seen as the result of the disk's thermal viscous instability. In a cold phase, hydrogen remains mostly neutral, opacity is low, and mass builds up in the disk. When a disk ring's temperature crosses the partial ionization point, opacity rises abruptly, boosting heating. This is the upper branch of the S-shaped equilibrium curve activating. A heating wave moves through the disk, pushing it into a hot, bright state for weeks to months. Then, as fuel is used up and cooling happens, a reverse wave turns off the light. X-ray bombardment of the outer layers shifts the thresholds and extends the plateau. In deep, quiet periods, the inner disk can evaporate into a hot, diffuse outflow like an ADAF, and radio jets activate during transitions. The same physical principles, stretched out over years, are discussed for active galactic nuclei as a way to explain changing look. The disk accumulates matter for a long time, then spends it quickly, and the corona and winds join in with changing chords. Fact 79th. The cosmic X-ray background, a faint sky curtain peaking around tens of keV, has been identified as the collective signal from billions of active nuclei, including those that are obscured. To gather its spectrum, sources with high absorption and Compton thickness, with NH columns above approximately 10 to the 24th centimeters to the -2, are necessary. Their direct light is absorbed, but reflected and leaked photons build up power at high energies. Synthetic background models are assembled by combining quasar luminosity functions, absorption distributions, and their evolution with redshift, aiming to match the spectrum and the number of observed sources. Deep surveys by Chandra and XMM have resolved a considerable part of the background at soft energies, while NuSTAR has contributed the hard KeV, illuminating the population of hidden nuclei.
Via the Sultan argument, the AGN luminosity integral is connected to the total hole mass today, yielding an average radiative efficiency of tenths, indicating significant spins in a substantial fraction of the central massive objects.
Fact 80. The signal from black hole mergers encodes physics via its frequency and amplitude, which grow according to a law determined by the Chirp-Vass mc equals m1 m2 to the 3/5 divided by m1 plus m2 to the 1/5. This mass is determined with the highest precision. The mass ratio, precession, and spins are more challenging to discern. A key derived quantity is the effective spin chi-f, which represents the average projection of spins onto the orbital axis weighted by their influence. A consistently positive value for chi-f suggests aligned spins and possibly an isolated evolutionary history. A chaotic distribution, on the other hand, points towards dynamical formation of the binary. Although signs of eccentricity are usually minimal by the time of detection, their search continues. Unusual harmonics in the signal would indicate a recent dynamical close encounter. The precision of locating the source on the sky is improved by employing a network of detectors. 3 or more observatories can constrain the search area to tens to hundreds of square degrees. Even in the absence of light emissions, these dark sirens can, in principle, statistically calibrate cosmology. This is done by comparing volumes containing galaxies with their catalogs, providing another avenue to extract cosmic information from gravity itself. Fact 81. The photon ring is distinct from the thick, glowing rim seen in shadow images. The observed ring is an accumulation of radiation from the disk and corona, broadened by turbulence and the interferometric aperture. The actual photon ring is made up of subrings, rays that have made 1, 2, 3, or more circuits around the black hole contribute increasingly subtle and weaker signals. Theory anticipates a nearly geometric decrease in brightness and an exponential narrowing of width from one subring to the next. Their form and shift are responsive to the system's mass, spin, and tilt. To isolate them, very long baselines and frequencies that minimize interstellar scattering are necessary, along with precise closure phases. Characteristic zeros and a comb should emerge in the visibilities. The detection of subrings will change the shadow from an attractive image into a precise ruler of Kerr geometry, separating plasma effects from pure gravitational effects. Fact 82. Microlensing of quasars serves as a natural scanning tool, enabling stars in the lensing galaxy to examine the accretion disk in the background. As a caustic moves across the source, different radii and sectors are amplified repeatedly. The law governing the disk size as a function of wavelength, r of lambda, is deduced from the flash's color and timing. For a Shakura-Sanyev thin disk, the expected relationship is r being proportional to lambda to the power of 4/3. However, observations frequently show larger sizes and more gradual temperature gradients, suggesting the involvement of scattering, the corona, and irradiation. At times, a caustic catches a reflected part. The K-alpha iron line flows and warps as if from local lighting on the inner edge, acting almost as a laboratory for a relativistic line at cosmological distances. When combined with polarimetry and continuum delays, this method grants unusual access to the disk and corona's two-dimensional structure, bypassing the need for spatial resolution, as gravity itself outlines the glowing film near the horizon. Fact 83. Not all stars near a supermassive black hole are destined for a bright tidal disruption. The Hill's mass is a key factor. If a black hole is too massive, its tidal radius is inside the event horizon, causing the star to be swallowed without an electromagnetic show. For a non-rotating black hole, this limit is typically tens to hundreds of millions of solar masses for a Sun-like star. A fast spin and a prograde orbit can increase this boundary, allowing more massive objects to be disrupted. Conversely, interactions between an intermediate mass black hole and a white dwarf are predicted to cause particularly hot events, where the dense, compact star might survive a thermonuclear explosion during disruption, emitting in the gamma-ray and X-ray bands. Partial disruptions on eccentric orbits can also occur, leading to repeated, smaller bursts. The observed distribution of tidal disruption events, TDEs, aligns well with these restrictions. The most massive cores have fewer flares, and spin and geometry are the unseen directors of these final events. Fact 84th. The paradox of youth in the galactic center is how O and B stars could be born where the black hole's tidal forces should impede assembly. Disk structure observations suggest an answer. At some point, enough cold gas arrived at the core to form a self-gravitating ring disk in its plane. This disk cooled, developed instability spirals, and broke up into stars right near the horizon. This created a top-heavy initial mass spectrum, meaning too many massive stars, as models of dense, irradiated environments predict. Signs of this scenario are also seen in other galaxies. Maser Keplerian disks and infrared rings tens to hundreds of parsecs from their centers. Another way is for a compact young cluster to be brought in, which then slides to the center, losing energy through friction. Some stars get stretched by tides, while others survive on extended S-family orbits. Both methods can happen together, explaining how a nursery is possible on the edge of a gravitational abyss. Fact number 85. The corona of an accreting black hole is a hot plasma, specifically electron-positron plasma, with temperatures in the range of tens to hundreds of keV. In this environment, soft photons from the accretion disk undergo multiple Compton scatterings, causing them to gain energy and form a high-energy tail. The temperature and optical depth of this plasma are not arbitrary. They are governed by physical processes. When the compactness, represented by L equals L sigma T divided by RMEC3, becomes high, electron-positron pairs are produced rapidly in an avalanche-like manner. This pair production increases the optical depth and leads to cooling, a mechanism referred to as the pair thermostat. Consequently, the observed spectrum shows an exponential cutoff at energies typically between 50 and 200 keV, which is consistently detected by hard X-ray observatories. During flares, this spectral cutoff shifts, implying that the corona's height or density is changing. The exact geometric configuration of the corona remains a topic of ongoing discussion, with models suggesting it could be a compact lamppost above the black hole's axis, the base of a relativistic jet, or a flat, sandwich-like corona lying above the accretion disk. By analyzing polarization, reverberation time lags, and reflected radiation components, scientists are building a comprehensive picture. The corona is compact, spanning only a few to 10 gravitational radii. It is rich in electron-positron pairs, and it likely participates in the magnetic energy processes that drive the jet. This connects the microscopic physics of pair creation and interaction with the large-scale phenomena of jets. Fact 86th. The hypothesis of cosmic censorship proposes that singularities, if they emerge, are concealed behind the event horizon. Theoretically, it is appealing to overspin a black hole, granting it a spin exceeding the Kerr limit or adding a charge. In such a scenario, the horizon would vanish, exposing a naked singularity. Traditional thought experiments, starting with the argument by Wald, demonstrate that nature creates hindrances. Particles with the requisite parameters either do not reach the horizon or, due to back reaction and radiation, abort the attempt. Similar conclusions are reached through calculations that account for gravitational self-interaction and superradiance. The system self-protects by preventing trajectories that make the parameter A is greater than 1. In astrophysics, magnetic and photonic feedback from accretion is also a factor. Disks and coronae remove angular momentum more effectively than they increase spin. Observations also do not reveal any naked objects. Images of the shadow, ring-down spectra after mergers, and the absence of stable optical or X-ray surfaces are consistent with the existence of a horizon, though perfect proof for censorship has not yet been obtained. The 87th fact states that a star's tidal disruption is not a quick splash into a disk, but rather a complex process involving shocks and orbital mechanics. The torn gas streams first travel back towards the pericenter along elongated elliptical paths. Because of general relativity's precession, their apsides are shifted and head-on collisions result in internal impacts referred to as stream-stream shocks. When precession is substantial, the gas circularizes rapidly, causing X-ray flares to appear immediately. Conversely, if precession is minor, the gas lingers in stretched orbits, releasing energy at a greater distance from the event horizon. In these scenarios, optical and ultraviolet light, along with powerful stellar winds, become the primary emissions. The black hole spin and the orbital tilt define the geometry, which can include dissipative nodes located far from the central object. The presence of helium and nitrogen lines, including bow shock fluorescence and broad asymmetric profiles, indicate the locations of heating. Radio observations occasionally point to a jetted mode of activity. Warm dust emits an infrared echo, effectively mapping the three-dimensional scene. In summary, tidal disruption events, TDEs, function as a laboratory for investigating not only gravity, but also the nonlinear gas dynamics of circularization within a strong gravitational field. Fact 88. A thin disk does not exhibit Newtonian viscosity. It is driven by the Balbus-Hawley magneto-rotational instability. A weak magnetic field in a differentially rotating gas causes adjacent rings to behave as if connected by springs. The inner ring pulls the outer ring forward, losing negative angular momentum and moving inward. The outer ring slows down, carrying the moment away. Subsequently, a turbulent cascade is initiated, and the transport of matter in the middle layer is more conveniently characterized by the parameter alpha, representing the effective stress relative to pressure. However, alpha is not universally applicable. Its saturation is dependent on the field's topology, particularly on the presence of a net vertical flux. With a large magnetic flux, the disk enters the MAD, magnetically arrested disk regime, where accretion is impeded by the field at the horizon, and the jet is amplified. With a small magnetic flux, in the sane, standard and active regime, the jets are weaker and the corona is more tenuous. GRMHD simulations that include light transport reproduce observed spectra, polarization, and variability, suggesting that powerful radio galaxies and blazars indeed operate with disks that have a significant magnetic flux, acting as the batteries powering the Blanford-Zanayak mechanism. Fact 89th. Identifying a black hole versus a pseudo-hole with a solid surface. If an object does not possess a horizon, infalling matter would be forced to halt and heat its surface, emitting thermal energy. This is particularly evident during inactive periods when the X-ray corona weakens. Observations show that black hole X-ray binaries in a quiescent state are many times dimmer than neutron stars, given similar accretion rates. This points directly to energy escaping past the horizon without thermal reflection. Further support comes from the absence of stable surface features or bursts, like thermonuclear bursts, and from shadow imaging. The contrast and size of the shadow are consistent with a gravitational shadow, not a luminous crust. Efforts to detect echoes in gravitational waves, which would be post-merger repetitions from a supposed reflective shell, have not produced stable signals, though the current limits are not absolute. The cumulative evidence is considerable, but it should be stated that these are empirical negative proofs. The final judgment will be based on increasingly accurate shadow maps, polarimetry, and ring-down spectroscopy. According to the 90th fact, not all massive stars perish in a grand explosive display. A portion likely collapses quietly, a phenomenon known as a failed supernova. In such instances, the star's core collapses, generating a weak shock wave, and its outer layers partially rebound. This results in the formation of a black hole with a minimal initial impetus. Indirect evidence for this includes the disappearance of red supergiants with virtually no trace. Faint transitional bursts exhibiting brief envelope inflation followed by a period of silence, and the demographic study of binary systems revealing massive components in close orbits without clear indications of a significant impact. Factors such as metallicity and rotational speed influence the probability of this outcome. Stars with lower metallicity experience less mass loss from stellar winds and are more prone to retaining their dense cores. Rapid rotation and close binary interactions can trigger a common envelope phase, accelerating the eventual merger of nascent black holes. The initial kicks imparted during these collapses are less pronounced than those of neutron stars, which increases the chances of binary systems surviving until merger. This assembled narrative, pieced together from observations of vanishing giants, silent transient events, and gravitational wave merger statistics, illuminates yet another mechanism for the genesis of black holes. Fact 91. The most potent cosmic flashes, known as gamma-ray bursts, are commonly attributed to black holes serving as their power sources. Long GRBs, with durations over 2 seconds, are currently understood to arise from the collapse of a rapidly rotating massive star. The star's core collapses into a black hole, creating a hot accretion disk around it. Magnetic fields then launch a narrow relativistic jet, a process explained by the Blandford's-Nayak mechanism and similar theories. Short GRBs, lasting less than 2 seconds, are probably the result of neutron-star mergers or a neutron star combining with a black hole. Milliseconds after such a merger, a compact black hole with a disk and outflows also forms. The estimated isotropic equivalent energies are in the range of 1051 to 1054 ergs. After the initial gamma-ray peak, an afterglow follows, observable from radio to X-ray frequencies. Shock waves within the interstellar medium produce synchrotron radiation, and a jet break in the light curve indicates a narrow collimation angle. In short bursts, a kilonova is frequently observed, an optical infrared glow from the decay of R-process elements in the ejected material. Fact 92. Another matchmaker for stellar mass black holes is the dynamics of multiple systems. In hierarchical triples, the Kozai-Litov mechanism causes the inner orbit to pump up its eccentricity when the outer one is inclined. The pericenter shrinks, and gravitational radiation drives the pair to merge within the age of the universe. This pathway naturally yields mergers with residual eccentricity at high frequencies and chaotic spin orientations, unlike the family-isolated evolution where spins tend to be aligned. A similar effect also operates in nuclear clusters around a supermassive black hole. It acts as a helper, pushing binary black holes towards a merger through secular resonances. Observationally, this is sought by low values of the effective spin, chi-f, and by subtle harmonics in the gravitational wave signal that are sensitive to eccentricity. The picture emerges. Several channels coexist, and the statistics of events gradually reveal their proportions. Fact 93. Astrometry has initiated a covert search for nearby black holes. Should an invisible companion draw a star into a minor elliptical trajectory in the sky, highly accurate positional measurements will detect this waltz. In contrast to standard X-ray binaries where accretion makes the object apparent, here the companion might consume minimal material and remain undetected. The synergy of astrometry, radial velocities, and photometry provides the mass of the dark body and eliminates the possibility of a bright companion. These systems hold importance for two primary reasons. Firstly, they serve to calibrate demographic information. They help establish the quantity of stellar mass black holes in the solar neighborhood and their distributions concerning mass and orbits. Secondly, they indicate origin kicks. Based on spatial velocities and orbital inclinations, it is possible to indirectly assess whether the collapse was quiescent or accompanied by an asymmetrical detonation. This approach supplements microlensing and X-ray methods, filling the void between the galaxy's boisterous and mute black holes. Fact 94th. Black holes play an indirect role in the cosmological distance ladder. Quasars, acting as lamps powered by accretion onto supermassive holes, are bright enough to serve as convenient background markers for gravitational lensing by galaxies. When several images are observed, the source's variability appears in them with differing delays due to variations in path and gravitational potential. Measuring these time delays and creating a lens model allows for the calculation of geometric distance and an estimate of the Hubble constant, a technique called the time delay method. This method is sensitive to the mass along the line of sight and to stellar microlenses, which, incidentally, traverse the quasar's accretion disk, providing insights into its size and temperature distribution. This leads to an uncommon partnership. A black hole serves as a beacon for measuring the universe's scale, and microlenses offer a free magnification effect. While systematic errors are substantial and require meticulous calibration, the method has already become a distinct cosmological test alongside supernovae and the cosmic microwave background. Fact number 95. The era of black holes signifies the universe's distant future, a period when stars will cease to shine and galaxies will spread out. Stellar mass black holes are projected to evaporate through Hawking radiation over durations approximately from 10 to the 66th power to 10 to the 68th power years. Supermassive black holes will require much longer, an extraordinary 10 to the 99th power to 10 to the 101st power years, or even more, for evaporation. A key factor is that radiation temperature decreases as mass increases. Evaporation is inhibited while the cosmic microwave background is hotter than the black hole's temperature. Slow mass loss will only begin once the background has cooled. According to theoretical predictions, the final stages of evaporation for smaller objects are expected to feature a rapid increase in power and the expulsion of high-energy particles. However, the specifics of these events remain subjects of discussion due to the unknown nature of quantum gravity. A completely different conclusion is also possible if dark energy undergoes alterations or proves to be dynamic. It is correct to assert that, within our present comprehension, black holes represent the most persistent structures in the universe, and its ultimate luminescence will likely emerge from their final quantum utterances. Fact 96. Theoretical models anticipate that stars in the vicinity of a supermassive black hole will form a structure resembling a cosmic anthill, a steep concentration of density toward the center. In the most basic scenario, where all stars possess equal mass, this is recognized as the Bacall-Wolf cusp, characterized by stellar spatial density increasing approximately as r to the power of -7/4. However, actual galactic cores are multi-component. Heavier objects, such as black holes and neutron stars, due to mass segregation, settle deeper, forming an even steeper dark cusp. Lighter giants and dwarfs, on the other hand, are distributed more sparsely. Observations conducted at the center of the Milky Way exhibit discrepancies with theoretical predictions. Red giants show a deficit of mass near SGRA, which could indicate the removal of their envelopes through collisions and tidal forces. It is hypothesized that the true cusp is concealed among invisible remnants. Indirect evidence, including transient flares, the distribution of X-ray sources, and the presence of hypervelocity stars, supports the concept of a dark core. Therefore, it can be concluded that the theoretical cusp likely exists, but its visible components, the bright pins, have been degraded by evolution, leaving behind a gravitational rather than a luminous trace. Fact 97. Disks of active nuclei function not only as sources of material, but also as matchmakers for stellar mass black holes. In dense, viscous gas, solitary black holes become captured within the disk's plane. Through friction, they lose energy, form pairs, and migrate towards pressure zones, which act as traps where encounters are guaranteed. Gas tori align the orbits and spins of these black holes relative to the disk's normal. This enhances the likelihood of achieving a high effective spin denoted as XF greater than 0 and merging within cosmologically brief periods. Before the merger event, the surrounding gas can emit a faint electromagnetic glow observed as quasi-periodic oscillations. After the merger, an afterglow is seen. The newly created black hole, by piercing the disk, generates shock waves and temporarily increases the accretion rate. Current detections are still uncertain, as the signals are weak and can easily be mistaken for the inherent variability of quasars. However, the channel for generating mergers is physically plausible and predictable. It naturally results in mergers at z-values around 1 to 2, permits hierarchical replays, and potentially connects gravitational wave detections with rare, faint flares in the optical and X-ray spectrum. Fact 98. Gravitational waves, akin to light, can be refracted by masses encountered on their journey. Under strong lensing conditions, a single chirp signal will arrive as multiple copies, with time differences spanning seconds to days. For detection instruments, this signifies repeated events, characterized by identical masses and waveform shapes, yet differing in amplitude. On lesser scales, stars and black holes situated within the lensing galaxy perform microlensing of the signal. Consequently, the amplitude becomes frequency-dependent, manifesting as interference ridges within the spectrum. Such occurrences are not solely theoretical constructs, but represent expected, though rare, possibilities. The universe at considerable redshifts is abundant with lensing objects. The search is pursued by examining merger catalogs. Concordant parameters and characteristic signal modulations would furnish a lens identification and permit precise cosmological measurements. As yet, no definitive instances have been recorded, but the established boundaries are already influencing compelling domains. If lensing is substantiated, we will obtain a further instrument for tomographic analysis. These very black hole mergers will serve as reference points for constructing mass distribution maps along the line of sight, encompassing objects from galaxies to their stellar collections. Fact 99. Black holes are a testing ground for holographic ideas and field gravity dualities. In various strict models, such as anti-de Sitter space, the behavior of a black hole is equivalent to the thermal evolution of a quantum field theory without gravity on its boundary. The horizon's entropy corresponds to the number of microstates. The ring, after a merger, maps to the poles of correlation functions, and currents at the horizon are depicted in fluid dynamics equations, fluid gravity correspondence. The renowned viscosity limit n over s equals h over 4 pi kb, derived in these theories, is unexpectedly close to estimations for strongly interacting quark-gluon plasma in accelerators. This is not about specific quasars in the sky, but about principles, how quantum disorder is encoded by the horizon's area, and how information is processed into thermodynamics. An indirect yet significant outcome for astrophysics is that the thermodynamic laws of black holes and statistical physics align into a single, mathematically robust picture, a guide for calibrating both cosmic observations and laboratory counterparts. 100th fact. Black holes that are alone and wandering in the interstellar medium are almost invisible. Without a companion star or a dense cloud, they gather material through Bondi-Hoyle accretion, which involves rare gas and dust particles moving at speeds of tens of kilometers per second. For black holes with masses around 10 solar masses and a density of about 1 particle per cubic centimeter, the accretion rates are very small. The efficiency of turning this into radiation is also low in hot, sparse gas flows, as much of the energy is carried inward before it can become light. Consequently, their expected luminosity is a tiny fraction, less than a millionth of the sun's, and it usually appears as weak radio or hard X-ray signals. Therefore, they are searched for using different methods, by looking for stellar microlensing, by observing the wobbles in the positions of nearby stars due to gravity, astrometric effects, and by catching rare, brighter events when they encounter dense clouds. Future wide-field surveys in radio and X-ray wavelengths, along with precise astrometry, are expected to systematically identify these solitary objects. This brings the story full circle. From bright quasars to silent single black holes, their entire history is understood through gravity, and light is simply a common but not required sign of their existence.